Welcome back to our class today. We continue with the discussion on elliptic curves, and this time we look at Montgomery curves. These are slightly different from the common Westerese curves that I've been looking at, and we shall see where the difference is. Of course, we shall also see how to convert from one form to the other. So we begin by the definition of the Montgomery curves. The definition is given here. The Montgomery curve is just an elliptic curve given by this equation. We are defining it over a field F, just as we did for the short Westerese form. So there's a slight difference here. Remember, the short Westerese form was an elliptic curve of the form x cubed plus ax squared plus b. Now see where the difference is. That we have coefficient of y squared. This coefficient could be anything, could be 1, 2, 3, 4. Is any number of the field. Is any number of the field. And again, A is also another element of the field. Then plus x. This time we don't have a constant at this point. So what we have is x. So this is elliptic curve referred to as the Montgomery. And this is the definition. Now, one thing that we need to, again, as we did earlier, we said that for it to be, when you are defining elliptic curve, we said that it must be non-singular. So the condition that ensures that it's non-singular is this, that it be multiplied by s squared minus 4 should not be equal to 0. So then it becomes non-singular. So we say that if it's non-singular, then it's an elliptic curve. But if it is singular, then it's just a cubic a curve, but not elliptic. So for it to be an elliptic curve, then this condition must be met. That condition must be met. That it be multiplied into s squared minus 4 should not be equal to 0. Now, when we are looking at curves that are used in real life situations, we mentioned that the Montgomery curves are one of them. That these are used in real life situations. They are real life applications. And we also mentioned at that point that we have several curves, elliptic curves, that are employed in real life situations. We have, and every company has its own. For instance, we gave an example of Bitcoin, which has its own elliptic curve. Zcash has its own, and several companies have their own. And there are companies that use the Montgomery curves and so on. So what just changes are the parameters. In most cases, the parameters are what change. These constants are what changes. So when the constant change, then we come up with a different elliptic curve. We change the constant, again, another different elliptic curve. So every company has its own. And what I'm emphasizing, that Montgomery curves are very important because they're used in real life situations. They have real life applications. And why are they used in real life applications? We say it's due to the efficient arithmetic, and we'll be seeing how it's easy to add points in the Montgomery curves. It's easy to add. And then there is also the issue of the Diffie-Hellman key exchange. Again, it's easy in these Montgomery curves as opposed to the other curves. So in fact, I'm just talking about is what I've listed here. I've said, unlike the general Weierstrass form, the Montgomery curves have simpler addition law. And this, because there's simple addition law, this will ensures that there is efficient computation. There's efficient computation because it's easy now to add points in these Montgomery curves. The other reason, the other thing that we need to know is that the Montgomery curves are defined only for fields where the characteristic of F is not 2 or 3. So the characteristic of F should not be 2, should not be 3. I would again remind you what I mean by characteristic. Characteristic of a field is a positive number n, which when multiplied by 1 gives you 0. That is what it means, the characteristic. And of course, what this means is not actually just multiplication. What it means is that the characteristic of a field is that number n where when you add 1 n times, when you add 1 n times, you get 0. That's what it means, characteristic. It must be non-zero. So it's a positive number. This is a positive number, positive integer. So for instance, if our field is this, then we are asking us, what is n? N is the number of times you're going to add 1 to itself to get 0. 1, 2, 3, 4, 5. So you can see that our n in this case is 5. The number of times you're going to add 1 to itself to get 0. So that means we can write it as 5, 1 is 0, if the field is that. Now, so what we are saying is Montgomery curves will be defined on fields whose characteristic are not 2 or 3. So if characteristic is 4, we can get a Montgomery curve. If the characteristic is 5 and so on, if it's 7, if it's 8, we can get a Montgomery curve on that field. But when the characteristic is 2 or a 3, then in that field we cannot define Montgomery curve on that field. I think that is clear, therefore, as we proceed. In cryptography, of course, we'll be looking at larger fields, so there's no problem here. We're looking at larger fields, and therefore the fields we're looking at in cryptography are fields where we can always define Montgomery curves on. Another point that we need to just recall, and it happens for every elliptic curve, is that the points of this curve would form an abelian group, and that a point of infinity will always be the identity element. Point at infinity will also be the identity element. This happens with every elliptic curve, and it's happening also for the Montgomery elliptic curves. I've already mentioned how simple it is to do addition. And again, I'm just saying that addition and doubling of points on elliptic curves it's easy, and therefore this leads to efficient computation and also efficient scalar multiplication. Because when we talk of doubling talking of how do you get 2, 2p, for instance, 2p. So that is what we call scalar multiplication. How do you get a 3p? How do you get a 4p, and so on? So it's easy to do this in Montgomery curves. And therefore, this leads to very efficient calculations. That is a point I already mentioned, so just emphasizing that. Now, so we've seen the formula of the Montgomery curve. What is important now is to see whether it's possible to convert the Montgomery elliptic curves to the short Weierstrass elliptic curves and vice versa. That's what I want. Let's just once again, look at the formula of the Montgomery curves, and this is the formula. So we want to see whether it's possible for us to convert these Montgomery curves to the Weierstrass curve. And the Weierstrass curve, we know, the short Weierstrass curve is this. So we want to see whether it's possible to convert this to that and vice versa. That's what we want to see. And then after converting that, of course, there's always very good. It's always very good to know how to transform one curve to another curve. It's always very useful in cryptography. Now, so therefore, we're looking at converting between short Weierstrass and Montgomery forms of elliptic curves. One thing that I've noted is that all Montgomery curves, all of them can be converted to short Weierstrass. All Montgomery curves, any that you get, can be converted to short Weierstrass. But the opposite is not always true. The opposite is not always true. That what I mean by that is that not all short Weierstrass forms of elliptic curves can be converted to Montgomery. Not all of them. Just a few can. Just a few. And we'll be seeing why not all of them. So there are conditions that the short Weierstrass form should meet. There are conditions that it must meet for it to be convertible to Montgomery curve. But the Montgomery curve, any of them will be converted to short Weierstrass. So that is the point I wanted to emphasize. And of course, we'll be looking at that in a short while. Now, so how do we then convert from Montgomery? Let's just begin from Montgomery to the short Weierstrass, because we know that every Montgomery curve can be converted to short Weierstrass. Then later on, we shall now come to see which short Weierstrass forms can be converted. Now, for an elliptic curve in the Montgomery form over any finite field, its short Weierstrass form will be defined like this. So if you have this, you can get its equivalent in the short Weierstrass form like that. Remember, it's supposed to be y squared is x cubed plus x squared. Is it x squared or just x? Plus b. Ax plus b. That is the short Weierstrass form. It's supposed to be this way, not x squared. Now, this You can see the x here. So that means this part is our A. So our A will be 3 minus A squared out of 3B squared. And then this is a constant. And that constant will be given by that. Of course, the answer will be reduced to mod Q, where Q is mod G. So our finite field is Fg. So this is how we be calculating A. It's just 3 minus A squared, this A squared, 3 minus this A squared, out of this B squared times 3. That gives us our R. Then B, the constant, will be given by 2 multiplied by A cubed minus 9A out of 27B cubed. So if you have Montgomery curve, you can always convert it to the short Westerese curve using this formula. We'll see an example on how to do that later. But remember that formula. So we'll be calculating our R and B using the formulas we just said. I've already emphasized this point, that not all elliptic curves in the short Westerese form will be converted to Montgomery. Not all of them. So which ones can we convert? That is the point that follows. Which short Westerese forms, equations can be converted? So I've said for a short Westerese curve to be converted to a Montgomery curve, then it must meet the following conditions. The first condition is that its number of points must be divisible by 4. So if the short Westerese form has 8 points, this is divisible by 4. So the first condition has been met. So we proceed the second condition. But if it has 7 points, then the first condition has not been met. So we don't even look at it. It cannot be converted to a Montgomery. So that means the first condition is that its number of points should be divisible by 4. The other condition, that if the short Westerese form were to be converted to Montgomery, then this cubic polynomial would have at least one root. This cubic polynomial should have at least one root. Where am I getting this from? It's just this. It's just this. So I'm just saying that my root is Z, for instance. This cubic equation, should have one root, at least one root. So if you solve it, it means just equate it to 0. Equate it to 0 and see whether there is, or in fact, without equating to 0, what do we mean by having one root? It means you can get a value of Z, for instance. That's what I mean. You can get a value of Z such that when you substitute it here, you get 0. That's what it means by being a root. I hope we are together up to that. We are looking at conditions that the short Westerese equation must meet for it to be convertible, for us to be able to convert it to Montgomery form of elliptic curve. The last condition, there are only 3 conditions. The last condition is that this should be a quadratic residue. Should be a quadratic residue. We talked about this quadratic residue even yesterday, and we say that what it means that this equation, after substituting, you see you get a root here. You get a root here. So we are assuming that our root here is z0. We are assuming that our root here is z0. So that root, therefore, square it, the root you get from here, square it, then multiply by 3, then add a to it. A is just coming from here. Add a to it. The answer that you get should have a square root. That's what it means, quadratic residue. It should have a square root, mod q. We're using what? We're using g. Were we using g? Yes, we're dealing with the f g. So that whatever you get, first of all, you got some root here. This root squared, multiply by 3, add that answer to a, and then whatever you get should have a square root. If these three conditions are met, then it means that the short Weierstrass equation can be converted to Montgomery. If those three are met, then it means can be converted. Now, how do we then convert? Supposing the three have been met, those three conditions have been met. We've already seen how to convert the Montgomery to short Weierstrass. It's here, the formula is here. How to convert Montgomery, this Montgomery. How do you convert it to short Weierstrass? We've seen that, the formula is here. But now, how do we now convert the short Weierstrass to Montgomery? Assuming that the three conditions have been met, the formula is here. The first thing we do, we get S. And S is given by the square root of 3s squared plus b. Then you get the inverse, that is square root. First of all, get the square root. Where are we getting A and B? A and B are just from that equation of short Weierstrass, the short Weierstrass equation, A and B. So that A squared multiplied by 3. Then add it to 4b. The answer, get the square root of that. Of course, you're doing it mod q. Mod q, it was g, mod g. Doing it mod g. Get the square root, and then the inverse of the square root gives you s. Once you get s, write the Montgomery equation. This is the Montgomery equation. So s is multiplied by y squared, then equals to x cubed, then 3 multiplied by this was the root we obtained here. The root of this cubic equation, we call it z0. So that root multiplied by 3, then multiplied by this s, then multiplied by x, and square what you get, square what you get, then add x. This is how we convert the short Weierstrass form of elliptic curve to Montgomery. But of course, we've already said before you do this conversion, first of all, you have to check whether this short Weierstrass form can be converted. Before you convert. Converting is very easy. It's very easy. You only need first of all to check whether it can be converted. When you check whether it's converted, it can be converted. First of all, find out what is its order. How many points does it have? Does that order, is it that order divisible by 4? Is that order divisible by 4? If that is true, then go to what is on the right side there, on the right hand side of that equation. On the right hand side, we have a cubic equation. A cubic equation. Find out whether this cubic equation has a root. Find out whether it has a root. If it has a root, then the second condition has been met. Proceed the third condition. The third condition, take that root that you obtained from here, multiply by 3, add a to it, and see whether this has a square root. See whether it has a square root. If this is met, then you can now convert. You can now convert from the short waist arrays to Montgomery. How do you convert now? Take 3 multiplied by a square, add it to 4b, then get the square root of that, then the inverse of that square root. That you call it S. Then just come and do this, and you have the Montgomery equation. We just want to look at 1 or 2 examples to make these points clear. Of course, we need to know the Montgomery equations, elliptic curves, because they are very much applicable in real life situations. There's a lot of research on that. Our S there, S that we've been calculating, you will call it the scaling factor. That's what it's called. Why do we do it? And I've said the scaling factor normalizes the curve. And this is what that means, to normalize the curve. It means it will assist in keeping qualities like point addition and point doubling to be, it allows us to do point addition. It also allows us to do point doubling. So that is the essence of this scaling factor. So when you read books, you'll find scaling factor. That's what it does, and this is how we calculate that scaling factor. The scaling factor has another role, that it also ensures that the curve is specified over a field, and therefore it enables efficient arithmetic operations. And of course, I've already mentioned that we require these efficient arithmetic operations, or we require arithmetic operations to be efficient, specifically in applications of cryptography. We don't want arithmetic that would not be efficient. Of course, we want security, and for you to ensure that you have that security, then everything you are doing should be done efficiently, especially the arithmetic and so on. Okay, let's now look at examples. Consider this prime field and this short waist arrays form, and we are asked to determine the Montgomery curve. We are asked to determine the Montgomery curve. We have this short waist arrays. We are supposed to determine. You know what this means? This means this is just defining that our A and our B is what you put here. This is an elliptic curve, and the way I read it, this is elliptic curve where A is 8 and B is 2. So it's not something to confuse us. What we are interested in here is, can we convert this short Westerese form to Montgomery? And before we do that, we have to check whether it's convertible. We have to check whether it's convertible. If it's not, there is no need of converting. We cannot convert what is not convertible. So we begin by checking. The first thing we do, as we said, we check how many points does it have. Now we have codes. We have codes that we can try to check how many points this one has. So when I was checking, I discovered it has 16 points. Now 16 is divisible by 4. And therefore, our first condition has been met. Our first condition has been met. We proceed and check the second condition. We have 3 conditions to check whether it can be converted. When we find that all the 3 conditions have been met, we proceed and convert. But before that, we cannot. So the first condition has been met. It has an order that is divisible by 4. Order is 16. Order is 16, and this order is divisible by 4. So the next thing we check is whether this cubic equation on the right side has a root. Whether it has a root. So that one, you do it using your code, and the code will just be using trial. Remember, we are doing it mode 17. So the code will check whether 0 is a root, check whether 1 is a root, check whether 2 is a root, check whether 3 is a root, check whether 4 is a root, all the way up to check whether 16 is a root. So it checks by just substituting this one here. And it wants to see which of these would give us 0. So the one that gives us 0 is then the root. What do we mean by a root? We mean a solution to some equation. What is the solution to this equation? And the solution to this equation should give us 0 if you substitute that solution. So let's substitute 0. When you substitute 0, where there's x, you get 0 cubed, which is 0, then 8 times 0, which is 0, then plus 2. So the cubic equation, substitute 0. When you substitute 0, when x is 0, this gives us 2. So it means x 0. It means 0 is not a root. Remember, we are doing it mode 17. What about when x is 1? When x is 1, we have 1 cubed plus 8, that is 9, then plus 2, that is 11, gives you 11. So again, it means that 1 is not a root. It means that, because this would be 1 plus 8, that's 9, plus 2, that would be 11. So when I tried that, I tried until I reached 8. I tried until I reached 8, and so that would be 8 cubed plus 8 multiplied by 8, then plus 2. I discovered this gives me 0. Of course, that would be 0. You can see that 8 cubed, that is what I'm doing, then plus 8 times 8 plus 2, this gives me 0. How? It gives me 0 because you can see this is 64. That is 64. 8 times 8 is 64. I just want to find out on division by 17 what the remainder is. So I'm just opening my calculator. Just want to check. So I have 64 therefore. Divided by 17, because there are 3 times. Because there are 3 times, what is the remainder? and the remainder is 13. So this is like 13 times 8. This one I've already found to be 13 here. Then plus 2, 8 times 8 I already found is 13. Now, so what about 13 times 8? 13 times 8, 104. Then divided by 17, goes there 6 times. Goes there 6 times, and the remainder is 2. So this then reduces to 2. Then there's a 13. Then there's a 2. So 13 times 4, that is what I mean. No, not 4 times. 13 plus 4. That gives me 17. I'm doing this mod 17, so that is 0. So it means after trying, I found that 8 was a root. I do not mean that this is the only root. There could be other roots, but the thing is, at that point, what we are trying to find out, the condition was that that cubic equation should have at least one root. That cubic equation should have at least one root. So it has one root. We found that the root, it has 8 as the root. So 2 conditions have been met. The first condition was that the number of points of this curve should be divisible by 4. And the other condition is that the cubic equation on the right of this elliptic equation should have at least one root. Let's just go back there. Yes, it says the polynomial this has at least one root, should have at least one root. It's not saying that you find all the roots, just saying ascertain that it has at least one root. We've ascertained that it has one root at least, and the root we found is 8. Now, so from there, that root that you found, you now use it. The third condition. The third condition that is a third condition, is that it should have a square root. And this our Z naught, there is the root. The root we just obtained. So we found our Z naught to be 8 in this case. It's the root. And then A, what is our A? We go back and to the equation. Go back to the equation. And our A is 8 also. Our A is 8 also from the equation. So now, just substitute. Just substitute 8 square. And we found it to be 13 just above. We found it to be 13. Found this to be 13. So we're talking of 3 multiplied by 13, then plus 8. 3 multiplied by 13 is 39. 39 plus 8, this is 47. And we are doing this mod 17. So you're asking ourselves, 17 want to go here. What will be the remainder? I'm seeing that 4, something goes there 2 times, I think. Then you get that 4, the remainder will be 13. That's what I got. So whichever way you use, you should get the same thing. The remainder is 13. Now, so the question is this 13 a square? In other words, does it have a square root? Does this 13 have a square root? You don't need to get the square root at this point. We are not asking even for the square root at this point. Just asking, does it have a square root? Of course, you'll require to get the square root later. But the question is, does it have a square root? That is what the condition talks about. Let's go back to the condition. What does the condition say? The condition says that it must, this value must be quadratic residue. This value should be a quadratic residue. So how do we get quadratic residue? Mod P. How do you get quadratic residue mod P? Is given by, no, how do we tell that something is quadratic residue mod P? So A is a quadratic residue mod P if A raised to P minus 1 divided by 2 mod P is 1. A is a quadratic residue if A raised to P minus 1 divided by 2 mod P is 1. So at this point, we'll be using fast powering algorithm. But if this gives you -1, then it's quadratic and residue. If it gives you 0, then it just means that this value is divisible by P, and therefore, again, is a quadratic residue. So in our question, our P was 17. So then we are talking about A raised to 17 minus 1, which is 16, divided by 2, that is 8. Mod 17. We want to see what we get. If the answer is 1, then it means that A is a quadratic residue. So our A in this case, is 13. So I want to see whether 13 is a quadratic residue. So it means 13 raised to 18 mod 17, what do you get? So if you get 1, it means it has a square root. It means it has a square root. And so all the 3 conditions will have been met. So far, you have 2 conditions already satisfied. So I want to find out whether 13. So in fact, I used the code for fast powering, and it just gave me 1 straight away. But of course, what I was doing was this: 13 raised to 1 is 13. 13 raised to 2. So what you're doing it mod 17. So 13 times 13. Just do that fast. 13 times 13 is 169. Dividing that by 17 goes there 9 times. And the remainder is 16. The remainder is 16, which of course you can call -1. You can call it -1. It's easier that way. So, but what we want is 13 raised to 8. This will be the same as 13 raised to 2, then raised to 4. It's the same as that. But 13 raised to 2, we just found it to be -1. When raised it to 4, you get 1. Because it's a negative number raised to an even number. When you raise that even number, you get that. So that's what you get. So it means, therefore, 13 has a square root. It means, therefore, 13 has a square root. So the 3 conditions have been met. What now follows is to convert the short way is to raise equation to Montgomery form. And our formula was here. Our formula was here that the first thing we do, just get S. And then the square root of the square root. We get this, the square root of that is S. Then you just substitute S in that equation. So it's a very short thing actually when you know the steps. It's a very short thing when you know the steps. So let's calculate our S. Our S will be given by that. That is a formula. So what is, we had found an 8 here. Z naught was 8. And then when you square it, we got 13. Z naught squared got 13. It was 8 times 8 gave us 13. Mod 17. That 13 multiplied by 3 is 39. Add 8 to it. We had done this one earlier, and the answer we were getting was 13. When you divide this by 17, the remainder is 13. So that is the 13 you're seeing. What follows is the square root of 13. We've already seen that this 13 has a square root. That's what we've been doing there. So it has a square root. So we proceed and find the square root of 13. This you can do by trial. You can do by trial. You see, the square root of 13 should be one of these numbers, all the way up to 16. Since we are working mod 17, it must be one of these numbers. So you are just trying 0, even the code will be doing that. Try 0, try 1, try 2, try 3, all the way. So when you try up to 8, you find that 8 is the square root of 13. From here, we had found that 8 times 8 was 13, mod 17. So it means, therefore, the square root is the square root of 13 is 8. The square root of 13 is 8. Now, the inverse of this is what we call S. The inverse of the square root of this is what we call S. How do we get this inverse of 8? You're using the extended Euclidean algorithm. The extended Euclidean algorithm. Of course, we also use the code to find the inverse of 8. You can also use trial and error. You're trying 0, 2, 1, 2, 3, all the way up to 16 and see which one, when you multiply by 8, gives you 1. Or you can also use the Fermat's little theorem. The Fermat's little theorem. But when you do that, you find that the inverse of 8 is 15. The inverse of 8 is 15. Because this sum gives you 1. So our S, therefore, is 15. So now substitute in the formula. Just substitute in the formula. Substitute S in this formula. So where there is S, put 15. Where there is S, put 15. And this was 8. But there's one thing you must know here while you're getting the square root. While you're getting the square root, see the square root is not only 8. The square root of 13 is not only 8. It's supposed to be plus or minus 8. We have picked the positive part. The negative part is supposed to be negative 8 plus 17. Because you're doing it mod 17, which is 9. So we picked this. So you will also have picked this. You will have picked this. There was no problem. You would have picked this, but we chose on this. We shall come back and choose on this. So that means, what this means, therefore, that every Westerese form of equation, if it happens to be convertible to Montgomery, then it will have two equations. We can obtain two equations, Montgomery equations, for every Westerese equation that is convertible. Every Westerese equation that is convertible will give us these two. That is where the square roots are different. Okay. So where was that? So we were in found 15. It found 15. 15 was our S, and so we substitute it here. 15y squared plus x cubed. Then our 8 here, multiplied by 3 will be 24. Then multiplied by 8, our S. 3 multiplied by 8, huh? Our S is 15. Our S is 15. So 3 times 8, our Z naught. This was our root. Then times our S. This answer reduces it to mod 17. Then multiplied by x squared. You arrive at that as the Montgomery equation. Now, so after finding the Montgomery equation, we can also obtain the points of this Montgomery equation. How do you obtain points? You just want to find what is x what is y when x is 0? What about when y, y when x is 1, when x is 2, all the way when x is 16. Just want to find. I don't know whether you've realized that this equation, you can multiply by the inverse of 15 on both sides. The inverse of 15, what was the inverse of 15? 15 was the inverse of 8. 15 was the inverse of 8. So that means the inverse of 15 is also 8. So you can want to even multiply by inverse on both sides. When you multiply by inverse on both sides, you come up with this. 8x cubed plus 24. Then plus 8x. So when you have this, it's easier to find y. It's easier to find y. So let me just show you. Write it properly. Because I want us to get points of Montgomery equation. So you have the Montgomery equation, and you're supposed to get its points. How do you get its points? This is a Montgomery equation up to here. So when you multiply the inverse of 15, you arrive at this. So how do you get the points? You must get y square, then y square, and then y. So when x is 0, this becomes 0, this becomes 0, this becomes 0. So y square is 0. The square root of that is also 0. So that we come up with the point 0, 0. The point 0, 0. So you'll notice that when x is 1, this becomes 8 plus 7 plus 8. 8 plus 7 plus 8. That is 16. 6. Get 6. What's this will be 16 negative 1 plus that which is 6. But this 6 has no square root. This 6 has no square root. So when x is 1, we do not get the equivalent value of y. It's not there. So there's that coordinate does not exist. So again, when x is 2, the value of y square that you get has no square root. When x is 3, when x is 4, the same thing. But now when x is 5, when x is 5, I get a value that has a square root. So when x is 5, you substitute there, 5, 5, and you get that we can get a value. And that value, there, it is square root of either 5 or 12. So that we come up with these 2 points. When x is 6, the value of y square has no square root. But when x is 7, the value of y square has square root, 7 and 10. So you come up with that point. So this, you're doing it by trial, of course. Again, the code will just be doing that. I'll show you how the code does it. So the code will just be doing that. I've already said that every Westerese equation that can be converted to Montgomery would have 2 equations, Montgomery equations. And the reason is just from where we're getting S. Where we're getting S, you see S was a square root. S was a square root. So S being a square root, we have 2 values of S. So the square root of 13, this S was the square root of 13. The square root of 13 is either 8 or negative 8. So what we picked on is this, and we've already gotten the Montgomery equation for this. So we can now also pick on this, which of course we know is 9. So S can also be 9. So if S is, no, not 9, S can be, we picked, S is supposed to be the inverse of the square root. The inverse of the square root. So when you get the square root, you have 2 values. So the inverse of 8 is 15. So you can now get the inverse of 9 to give us another value of S. The inverse of 9 to give us another value of S. After getting that other value of S, we proceed with it to write the Montgomery equation. The inverse we're just getting by a Euclidean extended Euclidean algorithm. So the inverse of 9 is just 2. Because 9 times 2 is 1 mod 17. So the inverse of the inverse of 9 is 2. So our other S therefore is 2. So now substitute 2 there. And you have 2y squared and then is equals to x cubed, and then 3 times, this was 8, and now 2x squared plus x. Of course, this is -1, this is -1, plus this, get a 2. Is it? Yes. No, it's times, it's not plus, it's times. So -1 times this, you have -3. Mod 17, this is 14. It's 14. So this Montgomery equation. And if you want, again, you can get the points of this. They're not the same points as the ones you've gotten here. They're not the same points, they're different. Because we have 2 different Montgomery equations. You can see the points are here. They're different. Now, I want to just again pick one example, show you how to convert the short Weierstrass to Montgomery.
So the number of points are different, but are they the same? The number of points in both curves, both Montgomery
Yes.
curves.
Okay. Okay, let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 for this case. And remember the curve we had, the okay, let's count this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 also. So the number of points will be the same. Of course, they'll be the same as the number of points of the Weierstrass. The Weierstrass had 16 points. This one will have 16 points. If the Weierstrass had 20, okay. That was, the question was from who?
Oh, Kimani.
Kimani.
Yeah.
Is that okay?
Yeah.
The number of points will be the same. Okay, let's now again look at this. What to convert of course, converting from Montgomery to Weierstrass form is easier. So that is why you're spending more time on converting Weierstrass to Montgomery. Of course, we say that not all Weierstrass form equations will be convertible to Montgomery unless they satisfy the 3 conditions. But we also say that every Montgomery equation can be converted to short Weierstrass. And we gave the formula for that conversion. Now, so we've been given mod 13. And the short Westeros form. And the question is converted to Montgomery. The first thing we want to do is to find out how many points does it have. Do these points, are they divisible by 4? They're divisible by 4, the first condition would have been met. So we proceed and check the second condition. So I discovered that these had 20 points. It has 20 points. 20 is divisible by 4. The first requirement has been satisfied. We proceed and pick this and see whether it has a root. Pick it and see whether it has a root. So we want to try all values from 0, 1, 2, 3, all the way up to 12. And I'm using mod 13. Want to try and see which of these is a root to that. So we have x, we have y. You try 0. What we are trying is this, x cubed plus 8x plus. Want to see which of these, if substituted here, would give us a 0. And that is what we then call a root. When you try 0, 0 here, 0 here, you have an 8. So 0 is not a root. Try 1. 1 here, 1 here, you'd have 9 plus that. 9 plus that is 17. Mod 13, that would be 4. So 1 is not a root. So when I tried up to 4, I discovered that when x is 4, I'd then be talking about 4 times 4 times 4 plus 8 times 4 plus 8. And this gives me 0. Because 4 times 4 is 3. Then times this 4, times this 4, and you get negative 1. Get negative 1. Negative 1, what about this? This is, we are doing it mod 13. Doing it mod 13. And 8 here is negative 5. It's negative 5. 8 is negative 5. Multiplied by 4, you have negative 20. Negative 20 plus 13 is 7, negative. Then plus 13, again, that is 6. It's 6. So you're adding 6 here. Then plus 8. So negative 1 plus 6 is 5. Plus 8, that is 13. Mod 13, you get a 0. Just trying to simplify my workings, making numbers smaller. You don't need to do that. So I've discovered, therefore, we've also discovered that 4 therefore is a root. 4 is a root. This cubic equation has a root. The second condition has been met. Proceed and find out whether the third condition is satisfied. So the third condition, what is it? What is the third condition? Take the root that we've just obtained, square it, get 16. Mod 13, that is 3. This is where this is where I am. Take the root, square it. That would be 3. 4 times 4 is 3. Then multiply by this 3, you have a 9. Then add this a to 9. Get 4. Is it? You get 4. That's what I was getting. Get 4. I don't know whether there's anybody who's not seeing what we're talking about here. Let me again repeat. We have a root squared. Talking about 4 times 4, which is 16. Mod 13, that is 3. Then 3 times 3 will be 9. This 9, add A is 8 in our case. 9 times 8 is 17. Mod 13, that is 4. So we found that, of course, the third condition has also been satisfied. Because you can see very well that while there is a root, no, this is the second condition. The second condition has been met, that there's a root. What is that? Oh, yes. That was the second condition, there was a root. So the third condition was supposed to be, does this have a square root? Does it have a square root? That's the third condition. So we found that this part is 4. And of course, we know that 4 has a square root. The square root of 4 is 2 or negative 2. So the square root of 4, therefore, in fact, we know. Don't need to try, okay? But this part I was testing whether it has a square root. But this one has a square root. Without even testing, 4 has a square root. And it's 2 and negative 2. Or you can say 2 and 11. 2 and 11. What I was doing at this part, I was determining if 4 has a square root. I knew it had a square, but I just want to follow the same way of thinking as I did in the earlier question. That after you found this, determine whether your answer has a square root using the Euler's criterion. So what Euler's criterion says, therefore, that 4 raised to p minus 1 divided by 2 mod p, if it's 1, then it means 4 has a square root. If it's negative 1, it means 4 has no square root. So 13 minus 1, our p is 13. 13 minus 1 is 12. Divided by 2, you have 6. So want to determine whether 4 raised to 6 has, whether it's 1 or negative 1. That's what we want to determine. If it's 1, then 4 has a square root. If it's negative 1, 4 has no square root. If 4 happens to have a square root, then the third condition will have been satisfied. But if it fails, then that condition will have failed, and therefore we cannot convert to Montgomery. Now, of course, as we had anticipated, it has a square root. As you can see, 4 raised to 6 gives us 1. So the next condition, the next thing to do, therefore, is to determine our S. Because we've seen that the two conditions have been met, so we now proceed to determine our S. Our S, 3 times the root square plus A, get the square root, then the inverse of that. This one we've just done is 4. And the square root is 2 or negative 2. So we have 2 square roots here. In fact, it's 2 and 11. So first of all, I want to consider this. Then later, you can consider that. So get the square root of 2 mod 13. A number that multiplied by 2 gives you 1 when divided by 13 is 7. Because this will be 14. So this is 1. So this, the inverse of 2 therefore is 7. I said use Fermat's Leibniz theorem, but this one is very easy. You don't require that. But in cases where you're dealing with the huge numbers, then Fermat's Leibniz theorem comes in. So S is 7 in this case. Since S is 7, we go straight and substitute it in this equation to obtain this as our Montgomery equation. If you want to find the points, you proceed the same way we did, multiply by the inverse of 7 both sides. The inverse of 7 is just 2. It's 2. The inverse of 7 is 2. Multiply by 2 on both sides. So this will give you 2y squared. No, 2 times that will be y squared is 2x cubed, then 12x squared, then 2x. Then find the values of y when x is 0, the value of y when x is 1, value of y when x is 2, and so on. That's how you determine points of this. And of course, you're expecting them to be the same as the other points. So how many are they? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Of course, the curve we are converting had 20 points. Now, so of course, we had found the other square root to be 11. The other square root was 11. So you can get its inverse as 6. So if the inverse is 6, that is our S. And you substitute it in that equation, and you have the Montgomery equation. You have the Montgomery equation. So it's always good when you have these Westerese short form, convert them to Montgomery, because Montgomery is applied in a real life situation. Always applied in a real life situation. As I said at the beginning, we have companies that use it, that prefer to use Montgomery equation in elliptic curve for their security reasons. So it's easy. We shall be looking at other forms of equations that elliptic curve equations that are applicable in life. Now, so converting Montgomery to short Westerese is very easy. And given a formula, and our formula was this. You see, we have the Montgomery, and what we want is the short Westerese. And the short Westerese, this is the equation plus ax plus b. So our A is equal to that, and our B is equal to this. So that it's very easy. It's very easy. So just go back to the Montgomery equation and pick your A and B. And you can see that our B is this and our A is this. So take this to the formula. We have A and B, and of course we have mod 17, which will be assisting us to reduce. So to get our A, this small a, you take 3 minus a squared. our A is 13. And then 3 times B squared, B7, or B7, let's just confirm. Yes, our B7, and our A is 13. So just put them in that equation. Just put them in that equation. So this is okay. Now, just substitute thing is here. You must get the inverse of 11, because you cannot divide 4 by 11. You cannot divide 10 by 13. So you must also get the inverse of 13 and multiply. So what I'm saying is this. What I'm saying, when you reach here, it's the same as x cubed plus 4 times the inverse of 11 x, then plus 10 times the inverse of 13. So the inverse of 11 is 14, and the inverse of 13 is 4. So it's 4x times the inverse of 11, and then times plus 10 times the inverse of 13. So this times that will be 48, and we are doing it mod. It was mod what? It was mod 17. So that's how you do it, and then you come up with the short Westerese form. Now, so I want to stop there. I'll share the notes. Of course, there's a code after this for conversion. We'll look at that code again and try to customize it to do more functions. That's why I want to stop. Thank you.